Sound insulating floor systems. Let's review the impact sound insulation performance of different floor systems. When we consider carpet, it is a very effective impact noise reducing surface. Carpet is itself resilient, so it reduces the impact forces that are transmitted into the building structure. When hard floor coverings are proposed, such as timber or tile, a resilient layer is commonly used between this hard floor covering and the floor structure itself to reduce the level of vibration that's transmitted into the building structure and into other spaces below. The problem with a hard floor surface covering, it doesn't reduce that impact noise radiation into the space itself. That still remains. So the people within that space could be distracted or annoyed by that impact noise within the space. Generally, the more resilient or softer the interlayer, so whether it's carpet on the top of the surface or a resilient layer in between the floor surface and the structure, the greater the impact noise reduction. The addition of a resilient layer under a floor surface, products such as Regupol, Acoustimat or Laticrete, are examples, serves only to control the transmission of a generated impact noise in the internal space. Like I said before, in this case, an impact noise is still radiated to the originating space, and it will be almost clearly audible as if the resilient layer was not actually installed. In order to quantify structure-borne noise, the weighted impact sound pressure level unit is used. The LNTW is a single number rating used to compare the acoustic performance of floors and ceilings excited by impacts produced by a standard tapping machine. It's similar to the way we use RW and STC to measure the performance of airborne sound transmission loss. It is a weighted impact sound pressure level heard in the receiving space when a tapping machine is operating on the floor above. The tapping machine is a calibrated set of hammers that are driven by a motor to produce a standardized impact sound pressure level on the floor surface itself. The impact sound pressure level is measured in the receiving space in third octave bands, and it is compared to a reference curve, similar to the RW is compared to a reference curve. The lower the number, the better the performance. In the US, the alternative parameter to LNTW, or impact sound pressure level, is the impact isolation class, or the IIC. Again, it's a single number rating used to compare the acoustical performance of floors or ceilings when excited by the standard tapping machine. It is similar to RW by comparing the measured impact sound levels in third octave bands in the receiving room using the tapping machine, and is then compared to a reference curve. So the relationship between impact sound pressure level and IIC is as follows. LNTW equals 110 minus IIC in decibels. By being able to make this relationship between IIC and LNTW, it makes it easier to compare performances of different floors and ceilings that have been measured in different parts of the world. IIC could be considered more intuitive and comparable to an RW because the higher the IIC value, the better it represents impact sound insulation, just as a higher RW represents better airborne sound insulation. The value of 110 was selected to yield similar RW and IIC values for typical building materials. So let's look at the impact sound isolation various floor constructions to see what performance that we get. So the reference case would be a bare concrete slab or a base concrete slab. The measured impact sound pressure level is 75 to 80 dB, or an IIC impact isolation class of 30 to 35 dB. And the subjective performance indicates that impacts will be clearly audible and sounds will be thuddy and tappy sounding. If a direct fixed hard floor surface is then added to the concrete, such as stone or a timber floor bonded to the floor with adhesive, we still get quite a poor impact sound pressure level of 70 dB, or an IIC of 40. Impacts again are clearly audible, sounds thuddy and tappy. It's as if the concrete has not had any treatment added to it. If we add a hard floor surface to the concrete slab but include a resilient grout or a resilient adhesive to provide some sort of vibration isolation performance, we would get a slight improvement of 2 decibels. It has an increased floor depth of 2 to 4 millimeters to accommodate that resilient grout, but it still gives the same subjective performance. If we add a thin resilient layer to the concrete slab, and then add the hard floor surface on the top, a wooden floor or a tiled surface finish, we get about a 5 dB reduction in the impact sound pressure level. The impacts are audible, the sounds are still thuddy and slightly less tappy, but there is a noticeable reduction of 5 dB. So typical products would include a polysilent plus material from PCI, a soundproof underlay from ABA, or a Regupol K225 resilient mat. If we use a much thicker resilient layer, which adds 10 to 30 mil thickness to the overall floor construction, we get a lot better sound isolation performance, impact sound isolation performance. It starts to reduce from that 75 to 80 from the bare concrete slab or the bare floor on the concrete slab down to 55 to 65. So impacts would be audible occasionally, sounds would be thuddy but much less tappy. So an example product is a Regupol 6010SH. We start getting much better sound isolation performance from impacts when we use sound isolating battens. And this basically includes discrete resilient isolators under timber floor finishes or under tile surfaces. We get an LNTW of around 45 to 52, or we're starting to get an IIC of up to 58 to 65 dB. Where we want some serious impact or structure-borne sound isolation, we start looking at floated floors. And these are stone or wooden floors with a concrete screed, 40 millimetre deep discrete rubber isolators or resilient isolators on a base concrete slab. And then we start getting LNTWs of less than 45, and the subjective performance is that impacts are generally inaudible. And typical products include a Kinetics brand SR bespoke isolation system. But an alternative, a much cheaper alternative to getting much improved impact sound isolation is to put a carpet over the concrete. So although it doesn't give you that hard floor surface finish and that aesthetic that architects want, it gets you very high impact sound isolation performance. And it only adds 5 millimeters thickness to the overall floor construction. The subjective performance is that impacts are generally inaudible. So we've just looked at concrete floor constructions or a concrete base to the floor construction and then adding different treatments on top of that. Timber floor build-ups, on the other hand, are very difficult to assess in terms of impact sound insulation performance. The acoustic character or nature of timber floor build-ups differs significantly to concrete-based floors, where the construction of concrete is homogeneous and it is very predictable. Because of the use of floor battens and deep joists, there are also large cavities generally in timber floor build-ups, and these can generate low-frequency drumming noise due to the coupling of the floor surface with the air cavity behind. And retrofitting existing timber floors for impact sound isolation can uncover many issues. And guaranteeing the performance of timber-based floor systems is a very risky proposition. Here's a typical timber floor build-up showing what might be used to provide impact sound isolation. So starting from the floor surface, we have floor decking, which could be chipboard or ply or tongue and groove boarding on the top. Then we have a 75 by 175 joist, which is connected to a plasterboard ceiling underneath via some 50mm battens. What is installed in the cavity is acoustic insulation to try and reduce that drumming noise formed by the air cavity between the floor surface and the joists. Here's the impact sound isolation performance of some timber build-ups to give you an indication of how they compare with concrete build-ups. So this construction detail here would have a floor finish on the outside, a 9mm compressed fibre cement sheet, a 5mm resilient underlay, a 9mm compressed fibre sheet again. You'd then have a 21mm existing floorboard, an air gap which has 50mm insulation in the cavity, and then 2 layers of 13mm fire-rated plasterboard on the ceiling side of the space below. This is quite a complex and considerable build-up, and it gets an impact sound isolation of LNTW of 45. So when you compare that to a concrete slab with carpet on top, you're getting the same performance with a much more complex construction build-up. Also, the depth of the construction is quite large as well, with a 307mm total thickness of the floor. To get some improvement on this, you would then add different layers of fibre cement sheet to provide extra mass. There's an extra layer. There's 2 9mm layers of fibre cement sheet, and we've made the plasterboard thicker on the ceiling side. We've also included ceiling spring isolators, which again, because the ceiling is hung resiliently from the joists above, it is trying to control that structure-borne noise path of impact noise from the floor above through to the receiving space below. So the improved performance is only by 3 dB. And in this case, you can see the sound reduction index for airborne sound is approximately the same at 58 dB.